Good morning, everybody. Today begins the beginning of the rest of the semester. We are setting the mold for what we're going to be doing nearly every lesson from now until June, hypothesis testing, which begins with the title of today's lesson, calculating the probabilities of type 1 and 2 errors. But first, let's talk about this hypothesis testing. What is hypothesis testing? It is basically an argument between you and a friend of yours. Basically, you say this, you have a claim. Yeah, well, I believe this. And your friend says, oh, yeah, well, I think you're full of it. And I think it's this. And then you say, oh, yeah, well, prove it. And then your friend says, oh, I will. And then you says, okay. All right, well, it's not really like that, but it's kind of. So let's go through the steps of hypothesis testing. Here they are. We formulate a simple null hypothesis. The null hypothesis is the original claim. And we're going to call that, oh, it's actually pronounced H naught, but we're going to call it HO. All right, we'll call it HO, the null hypothesis, which is an assumption about the population, which may or may not be true. And then your friend makes an appropriate alternative hypothesis, and that's going to be called H1, which is to be accepted when the null hypothesis is rejected. Okay, so after you make your claim and after your friend makes the alternate claim, we specify the probability of a type 1 error. What is a type 1 error? It is rejecting the null hypothesis when it should be accepted. What if you are correct all along, but your friend is very persuasive and they persuade you to say that you are wrong, the original claim is wrong. However, it was true all along. Guess what? An error was made, a type 1 error. That's half of what we're talking about today. So step number 3. Based on the sampling distribution of an appropriate statistic, we construct test criterion for the null hypothesis. This sounds all very difficult. You know what it really means? It really means this. If you're testing means, and you know what sigma is, what's the test criterion? It's Z. What if sigma's unknown? And that's T. Hey, what if you're testing proportions? Hey, that's just Z. Hey, what if you're testing variance or standard deviation? Then that's chi squared. We spoke about yesterday. So that's step 3 right here. Step 3 is just choosing the test criterion. Step 4, actually calculate Z or T or Z or chi squared. And based on the calculation of the test statistic, we decide whether, whether Z is really, really big or not big at all. We decide whether to go with the original claim, the null, or the alternate claim. That's it. That's hypothesis testing. We're going to be doing that for the rest of the semester. Really not so bad. All right, so statement down here. Statisticians aim to be as confident in their conclusions as possible, but errors are inevitable, and they happen occasionally. There are 2 types of errors that can be made. A type 1 error. We already just talked about that. The mistake of rejecting a true null hypothesis. Type 2 error is just the opposite. It's the mistake of accepting. We're not going to use the word accept. We're actually, throughout the semester, going to call it fail to reject a false null hypothesis. So you go along with the original claim even though it's not true. Obviously, we want both errors to be as small as possible, but the only way to decrease both errors is ding, 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 increase sample size. For any given sample size, decreasing the chances of one error, I should underline this, decreasing the chances of one error will increase the chances of the other. It's like a seesaw. If you want to decrease the chances of a type 1 error, the chances of a type 2 error go up. Statisticians have to deal with this balancing act throughout a test. Okay. So scenarios of these examples right here. So we're going to talk about our null hypothesis. Null hypothesis, which is the HO. We are either going to say that the null hypothesis is true or false. Mr. Colodi, how do we know if the null hypothesis is false? That's a great question. I'm glad you asked it. We'll get to that a little bit later. Then you're going to talk about your decision. You are either going to accept the null hypothesis, which we're actually going to fail to reject, or we're going to reject the null hypothesis. Okay, I'm going to call this scenario 1. Suppose the null hypothesis is true, and we accept it. Congratulations, you've made a correct decision. And the probability of that happening is 1 minus alpha. Wait a second, we've seen 1 minus alpha before. Yeah, it's the big unshaded region in the center of all our confidence intervals, right? But suppose, and I'm going to call this scenario 2, suppose the null hypothesis is true, but we reject it. Uh-oh, we rejected a true null hypothesis. That is a type 1 error. And the probability of committing a type 1 error is alpha. Wait a second, we've seen alpha before. Yes, alpha is just the shaded tails on both sides. So all this is not necessarily new, it's just that I haven't given it framework like this. Suppose the null hypothesis is false, but we accidentally accept it. Uh-oh, we've committed a type 2 error. And the probability of committing a type 2 error, it looks like the letter B, but it's actually the Greek letter beta. And last but not least, what if the null hypothesis is false and we reject it? Congratulations, it was false and you rejected it. You've made a correct decision. Yay. And the probability of that happening is 1 minus beta. And 1 minus beta is actually referred to something called the power of a hypothesis test. There are intermediate college stat courses that go very deeply into the power of a hypothesis test. The length that we're going to go into it is right there. That's it. So now, what's examples? What would be actual examples of each of these? All right, so let's just say that we are going to make a claim. And we're going to say that HO is that the average person does 9 hours of homework per week at Watchung Hills. Let's just say that. Okay, we have 4 scenarios. Let's go through examples of each. Scenario 1. Let's say that in scenario 1, we say that the claim HO that mu equals 9 hours is true. Then you go to a table at lunch. Oh my gosh, when are we going to be at lunch again? I hope soon. And at that particular lunch table, you got an average of, I don't know, 8.74 hours per week. And that would produce a z-score. I mean, 8.74 is really close to 9, so it'd be a negative z-score, but maybe like negative 0.2. I mean, it's nearly 0. It's because 8.74 is so close to 9. Here's the logic. Is 8.74 close enough to 9? Remember, it's called an average. Let me go on camera for a second. Remember, it's called an average for a reason. You're going to get some numbers a little above the average and a little below the average. It's an average. But is 8.74 close enough to 9 to accept 9? Chalk it up to chance? Or is 8.74 way far away enough from 9 to say, no way, 9 is bogus? I agree with you. You would accept the null hypothesis. You would say, you know what, 8.74 is close enough to 9. Scenario 2. What if the null that you do 9 hours of homework a week is true? And maybe you go to a table with senioritis, and that table only does 2.6 hours of homework a week. And that's going to produce a redonkulously low z-score, like negative 6.27. Now, if you find a sample mean of 2.6 hours, there's no way you're going to say that people do 9 hours of homework. You're going to say, well, no, 9 hours is too big. You're going to reject HO. You're going to reject HO, and unfortunately, that's a type 1 error. Okay, scenario 3. Now, what if the original claim that people do 9 hours of homework a week is actually false? How do you know it's false? Again, we'll talk about that soon. All right, and then you get a sample mean of, I don't know, maybe you go to the stats table and they do 15.6 hours of homework per week. I'm sorry, let me erase that. Scenario 3 is when we accept it. So say we go to the stats table and they do 10.3 hours of homework per week. And that produces a small z-score, maybe like 0.73. but 10.3 is still pretty close to 9, so we might accept HO. Unfortunately, it was false, so we made a mistake. By the way, this is correct right here. And finally, last but not least, scenario 4, suppose that the null that people do 9 hours of homework a week is indeed false. Okay, and we get a sample of just the absolute rigorous table. They're doing 15.6 hours of homework a week, and that produces a super high z-score like 5.62. Okay, you are so going to reject HO here. You're going to reject the null hypothesis, and you know what? Rightly so. Those are examples in the lunchroom of 4 different things. All right, so believe it or not, this example is your homework question. You have one and only one homework question, and I'm going to start it with you. Here it is. From a previous study, it was determined that in a certain metropolitan area, it takes on average 49.6 minutes to get to work. Sociologists who are conducting a present study take a random sample of 250 workers in the metropolitan area, and on the basis of this sample, decide whether the average is still 49.6 minutes. Specifically, accept the null hypothesis that mu equals 49.6 minutes if the sample mean falls between 48.4 and 50.8 minutes. Otherwise, the null hypothesis is rejected. From a previous study, sigma is 8.1. All right, A, calculate the probability of a type 1 error. B, calculate the probabilities of committing type 2 errors under all those values. And C, we have to plot something called an operating characteristic or OC curve. We're going to do all that, pieces of it at least. All right, so first thing I'm going to do is part A, type 1 error. I'm going to draw myself a little picture here. Okay, remember, this is the same picture that we've been drawing all along. Okay, so in this area right here is still 1 minus alpha. This is the area where you're going to accept HO. If you get a mean that falls anywhere within this unshaded region, that means it's not that far from the center. Remember, the center is right here. Okay, you're going to reject HO if you get values that fall out here or out here. And by the way, the alpha level split up into here and here. So alpha is just basically the sum of those 2 shaded areas, as it has been for days now. Nothing is different. But really, this is just a z-score question. If I really think about it, the mean of the sampling distribution, because we're taking a sample of 250 people, lowercase n is 250. The mean of the sampling distribution is still 49.6 minutes. I'm going to put that right in the middle, 49.6. Oh, by the way, this is 50.8, and this is 48.4, which means I should erase this down here because I don't want that to be there. Oops. I just erased the whole line. No. All right, there we go. This is 48.4. Okay, those are the barriers. We need to turn these raw scores into z-scores. And how do we do that? By using the central limit theorem. The mean of the sampling distribution is 49.6 minutes. The standard error is going to be the standard deviation, which is 8.1, over the square root of 250. And that gives me an answer. Actually, 8.1 over root 50 is about 0.51. All right, but let's just turn these into z-scores here. So I'm going to turn 50.8 into a z-score. So 50.8 minus 49.6 divided by 8.1 over root 250. And I get a z-score of 2.35. For the sake of time, 48.4 is equidistant. So it's actually going to be plus or minus 2.35. So this is positive 2.35. This is negative 2.35. I'll use a different color pen. That produces an area of 0.4906 on my z-table. And 0.4906 I subtract from 0.5 and I get 0.0094, 0.0094. I'm going to circle that. And I'm going to get 0.0094 over here. I'm going to circle that. So the probability of committing a type 1 error is 2 times 0.0094, which is 0.01, where is it, 0.0188. And that's it. Congratulations, I just did part A with you. You do not have to do part A for homework. I just did it with you. There it is, done. So really, it's just a z-score question. So now we move down to part B. Calculate the probabilities of committing type 2 errors for mu equals 47.1, 47.6, and so on and so forth. I created a table right here. And beta, remember, is the probability of type 2 errors. For homework, you're going to complete this table. I've started it for you. Well, I'm going to start it for you. How do you know if a null hypothesis is false? Remember, a type 2 error is accepting a false null hypothesis. You don't know it's false unless you have good reason to know that something else is true. So basically, you're saying, hey, what if 49.6 is false? What if 47.1 is the actual true number now? What if times have changed? So I'm going to do that with you right now. Okay, I'm going to draw a normal curve. And I am going to put not 49.6, but 47.1 in the center. Here's the problem. We are still running under the assumption that 49.6 is the actual still true mean. So we're going to accept 49.6 if we get values from 48.4 to 50.8. The only problem is on this graph, where is 48.4 and 50.8? 48.4 is probably right here. 50.8 is here. So this region right here, this is the region where we're still going to accept 49.6. The only problem is we shouldn't be accepting 49.6. Why? Because 47.1 is actually the true number. So this right here is the beta. This is the probability of committing a type 2 error. Basically, for homework tonight, you're just going to shade, you're going to find the shaded area between 48.4 and 50.8, but you have to put all of these numbers in the middle. So we have to find two z-scores here. It's going to be 50.8 minus 47.1 over 8.1 over root 250, over root 250. And you're going to calculate 48.4 minus 47.1 over 8.1 over root 250. And you're going to get two z-scores. You're going to get 1.57, and you're going to get 6.27. Okay, so let me write that there. 1.57 and 6.27. Those are the z-scores. If I look up 1.57, I get an area of 0.4418. 6.27 is off the charts, yo. So I get 0.4999. So to find my area here, I'm just going to do 0.4999 minus 0.4418. And I'll get my resulting area of 0.0581. And that is what goes right here. That's your homework tonight. Continuing to do that for all of these other values. The only problem is, let's say now, let me do a dividing line here. Now I want to do 47.6. So now I'm going to draw another curve, but I'm going to put in the center of this curve 47.6. I still need to find 48.4 and 50.8, which would be up here still, but closer to 47.6. Now I'm still finding this shaded region, but the z-scores will be different and the area will be different. That's your homework tonight. Then, last but not least, you need to put these things on a graph. And a graph that shows the probabilities of type 2 errors under various hypotheses is called an operating characteristic, or OC curve. So here's basically what you're going to do. We're breaking a graph. I'll do 47.1, 47.6, 48.1, 48.6, 49.1, 49.6, 50.1, 50.6, 51.1, and 51.6. And so this is mu if the HO of 49.6 is false. So 49.6 is false. What if these are true? And then over here is the beta levels. So 0.2, 0.4, 0.6, 0.8, 1, 0.2, 0.4, 0.6, 0.8, and 1. So I know that at 47.1, what is it, 0.0581? So I'll just put a dot right there, 0.0581. There we go. I just answered one piece of the OC curve with you. Your job is to find the rest of this table, put dots along where this should go, and then see what this graph should look like. I'll give you one guess. All right, just taking 21 minutes of your time. I hope you found this helpful, and ask questions if you have it. Bye.